We have defined so far an acid as a species that, when reacting with another, can donate a proton. In this case, this acid HA is donating a proton to water. In this case, water behaves like a base. An acid cannot exist without a base. So in this video we're going to study the types of acids and putting a lot of emphasis on the oxoacids. An acid will be an acid when this bond, the bond between the molecule and the proton that is about to be donated, is weak enough, and that means probably there is some electron density being pulled the other way so that that bond is being weakened, because there's going to be a transfer of a proton. The proton does not carry the electron to water, and this is why the conjugate base of an acid will be a negative charge, or one electron more. Okay, so what types of common acids we're going to see? And that's important that you memorize these, because you're not going to see in this course, at least, more than, with very few exceptions, more than these three types. The first type is the hydrides of halogens. So where X, it can be fluorine, chlorine, bromine, or iodine. Notice that typically these are gases. These are gases, so hydrogen fluoride, hydrogen chloride, etc. However, when they're bubbled, like for example chlorine in water, so this is gas, you bubble that. This does not only change its nature, it changes its name. This is called hydrogen chloride, this is called hydrochloric acid. Let me write it here. Hydrochloric acid has a very different behavior than hydrogen chloride in gas form, because hydrochloric acid can be deprotonated and works as an acid. Okay, that's something to keep in mind. We will talk about later that hydrogen fluoride is the only one that is not a strong acid, but keep it in mind, they're all acids. A second kind of acid that you will see is the functional group carboxylic acids. The carboxylic acid, you may be very familiar with it, is the conjugate acid of carboxylates, in which this bond is weakened enough because of the existence of the oxygens. This will release that proton and will form the carboxylate that it's also stabilized by resonance among the two oxygens, etc. These are carboxylic acids, being acetic acid, propionic acid, etc. Notice that all of them have this carboxylic acid in common. And the other ones that we're going to really put a lot of emphasis on is the oxoacids. The oxoacids has typically this form in which X will be an element of the upper right part of the periodic table: nitrogen, sulfur, phosphorus, chlorine, carbon, etc. Okay, and we will study a little bit the nomenclature of these oxoacids. We will also study the structure, because it's very important to understand why it is that some oxoacids are stronger acids than others. And also note that alcohols, at least in water, they do not behave like acids. An alcohol would have this structure. In water, do not expect this bond to be weakened enough to transfer this proton to the water. That does not happen. Alcohols are neutral, they do not behave as acids. The same for amino groups. If you think, well, nitrogen is fairly electronegative, why is it that this bond doesn't break in water to transfer the proton to water? This does not help either. This does not happen either. It actually acts as a base, as we will talk about in few slides. Okay, so let's talk about more the structure, about the structure of oxoacids. The structure of oxoacids is, as we said, the HXO, where X can be sulfur, can be nitrogen, chlorine, carbon, phosphorus, bromine, you name it. Okay, typically on the upper right part of the periodic table. The hydrogens are attached to the oxygen. Okay, and this means that these bonds have to be weakened in order to be released. And what factors do they intervene so that these bonds are weakened, so that it behaves like an acid? the most important factor is what we call the oxidation state. The oxidation state of the central atom. If you remember how we calculated oxidation state, typically you can calculate this by saying, well, the oxygen is going to keep all the electrons, excuse me, therefore the sulfur has no electrons in its valence, is a +6. The same for in here, nitrogen will be a +5. If you don't like the way it's being computed, think of if oxygen always has think of it as an ionic compound, so which is not, but if it were an ionic compound, oxygen has a -2 charge. -2 times 4, that would be -8. In order to compensate this -8, it means that you have 2 hydrogen, that is +2. To compensate the -8, you have to have a +6. Sulfur has a +6 oxidation state. Okay, and this will tell you that if sulfur is a +6, it means it's lacking a lot of electrons, is willing to attract a lot of electrons, so this means that sulfur can pull electron density its own way, weakening these bonds, therefore making sulfuric acid very acid. So what kind of questions can we ask knowing that? For example, what is it going to be more acid? Nitric acid or nitrous acid? Notice that nitric acid, as it's written up here, so there's going to be 3 times -2 from the oxygen is -6, 1 for hydrogen, that means +5 for nitrogen. Nitrogen is a +5 in terms of oxidation state. How about nitrous acid? Nitrous, if you calculate this, from the oxygen it will be -4 plus 1, it is a +3. So nitrogen is a +3. It means nitrogen +3 is less lacking in electrons. It will weaken less this bond. Okay, this means that nitrous acid is less acid because it weakens the hydrogen oxygen bond less. Okay, however, because in nitric acid, this nitric acid is a +5, it can attract more electrons because it's lacking. You can think of it as being very upset. It attracts more electrons, it weakens that bond, therefore is more acid. Okay, so how are they called? This is something that it's fairly important to kind of rationalize, even though at the end of the day you may just need to memorize it. The name of the acids depend on the oxidation state that we were talking about. If you calculate the oxidation state, you will see that this is +7, this is +5, +3, and +1. If you have in this case 4 different oxidation states, you will use the hypo OUS for the lowest oxidation state, and you will use the per and IC for the highest. Only the IC for the intermediate, for the second highest, and OUS for the third highest. Okay, so in this case, carbonic acid is, there's only one possible oxidation state, and this is the carbonic acid. Nitric and oxidation state is +4. So the default, it means that it's going to be the IC termination. Okay. Nitric acid, this is nitric acid and this is nitrous acid, and there's just two. This one is +5. If you, I'm doing it here very fast, but if you take the time, you will see that the oxidation state of nitrogen in nitric acid is +5 and in nitrous is +3. So if you have just 2 possible oxidation states, you will use the IC and OUS termination. Phosphoric acid. Phosphoric acid, in this case, this one again is +5. Phosphorus acid, this one is +3. Sulfuric acid, and again you'll be able to tell that phosphoric acid will be more acidic because it has a more high positive charge. It can pull the electrons more strongly. It weakens the bond with hydrogen more remarkably. The same goes for sulfuric acid and sulfurous acid. The oxidation state on the sulfur is +6 and +4, and this will be more acid, and this one will be less acid. Okay, and we will finish this this video, somewhat long video, but it's important to explain the oxoacids altogether by explaining that some oxoacids, if you count here, notice that some oxoacids have more than one proton to deliver. That means that these are called multiprotic oxoacids or multiprotic acids. So for example, in the case of sulfuric acid in water, you will have one first reaction in which water gets protonated, and you have something called hydrogen sulfate, and a second acid-base reaction in which you obtain a second hydronium ion and finally the sulfate. Alright, the same goes for phosphoric acid in water. It can give up to 3 protons. In this case, we will talk about that, but these are both strong acids. These both are strong acids, so that means they are completely dissociated to the right. Phosphoric acid, you'll have to memorize that in the next video. It's a weak acid, so we build the arrows as back and forth because only a certain amount will be dissociated, and so you have the so-called dihydrogen phosphate acid. The dihydrogen phosphate acid is even less acid than phosphoric acid, so, and when it gives 1 proton, it becomes hydrogen phosphate acid. And finally, the hydrogen phosphate acid can give a 3rd proton to become now the base phosphate. Okay, these are all weak. Okay, and notice that you could do the same, we're not going to do it here, for phosphorus acid. Okay, and you could you could do the same for sulfurous acid. Okay, in the next video we're going to memorize which ones are strong and which ones are weak. We can rationalize in terms of oxidation state, but at the end of the day it's easier and faster if you just memorize them.